of the torque. I just recall this thing. What is the equation for the torque? So stator voltage control is the first method to control the induction motor. So it means there is a relationship between stator voltage and the torque. So that equation we'll just bring here and we'll see what is that equation. We'll see that. Okay, so just recall the torque equation: 3 by omega s r2 dash by s r2 dash by s and v square r1 plus r2 dash by s whole square plus x1 plus x2 dash whole square. This is the torque equation. Now, if you observe this carefully, this is the voltage that is going to the stator. This is the torque. So, what is the relationship between these two? T proportional to V square. Is the relationship. So the torque is directly proportional to the square of the stator voltage. So, with this equation, from this relationship, we can conclude this thing that by changing the stator voltage, we can change the torque of the induction motor. So that's the logic here. Okay. So then what we do is now, so we'll just recall. So if you take, this is the speed and this is the torque. If you take, this is the speed and this is the torque. If you recall, what is the graph you will get here is, just recall what is the graph you will get here, because that will come from the speed torque characteristics. But the speed torque characteristics which we have discussed earlier, so in those cases, what we have taken, the speed we have taken on x-axis, whereas the torque we have taken on y-axis. So but now see here, as we took speed on y-axis and so you'll get something like this. This is the torque speed characteristics of the induction motor. Now we will draw some more graphs by changing the value of V. Then what we will get, the graph is something, we will get the graph like this. Something like this. So this is for V1, this is for V2, this is for V3. Okay. So obviously what is this is that V1 greater than V2 greater than V3. So when you go on increase the value of voltage, you see that the graph is moving upwards, or you can see the graph not upwards, the graph is moving right side. The graph is moving right side in the sense, for the same value of omega, the torque increased if you increase the voltage. That's the meaning of this. So this equation, we have drawn the graph here like this. Already we know the speed torque characteristics of the induction motor. So one graph we have drawn, then we go on increase the value of V. Then we got the set of graphs like this, where V1 greater than V2 greater than V3. Okay. So this way you can control this thing. But we have come here question that one important question we get. What is that question is that? So what is the means the question is now, what is the question is now that how do you just vary the stator voltage here. See, we understood that by varying the stator voltage, torque can be changed. That we understood theoretically, and from the equation and from the graph also. Of course, the graph has come from the equation itself. So from this equation, we can say that by changing the stator voltage, we can change the torque. That we understood. But what is the thing is that, here is that, how do you change the stator voltage? That's the question now left. How do you change the stator voltage? So to change the stator voltage, what are the possibilities we have? We'll just recall ourselves. How do you change the stator voltage? See here, there are several methods are there to change the stator voltage. Okay, we will see one by one. First of all, the stator voltage is AC voltage, because it's the induction motor is AC machine. So So it's AC voltage. So as it is AC voltage, as it is AC voltage, so you require something which can change the AC voltage. You require something which can change the AC voltage. So I will tell you one thing, that how can you vary the how can you vary the stator voltage, or how can you vary the voltage. I hope you know by this time that there are you might have heard this thing even in the power electronics course, that AC voltage controller. So AC voltage controller is one of the converters of the power supply. So what it converts? It converts one AC to another AC, one AC to another AC. So it converts one AC to another AC. That is the, I hope you know this thing, that what an AC voltage controller. So AC voltage controller will convert one AC to another AC. So the voltage it will vary. So when the voltage it is varying, okay. So how do you do that? Okay, we'll do one thing, that we'll take some example circuits, so that we can easily get that. So I will not draw the entire. I won't draw the entire induction motor circuit. Only stator I will draw, because the supply you will give only up to the stator. So that part only I will draw now. So many circuits. Lots of circuits are there. These are the stator windings. These are the stator windings. So now you see different types of AC voltage controllers. Now this is for, okay, this is for I'm just drawing the AC voltage controller circuit diagram here. Now you see now. So here you have the supply. Here you have the supply. Now these are the stator windings. Now what you do is, now by controlling the firing angle here, I hope you remember this single phase AC voltage controller. What it does. Uh, you have the load. This is single phase AC voltage controller. So by changing the firing angle of these thyristors, we have seen in the power electronics course is that the waveform will be. So what is the waveform? You will get generally if it is what is the output of AC voltage controller. Just recall the single phase. I will tell that you get something like this. Then this this is the output. So some part of that it is totally deleted. Means the firing angle alpha. Here the firing angle is alpha. So alpha is the firing angle. So at this firing angle, so this is thyristor 1, this is thyristor 2. So based upon that, you got this kind of effect. Now, if alpha is more, then this part will be shrink further. If alpha is 0, then that is same as the input voltage. So this is output voltage of your AC voltage controller. The same way here, as it is three phase induction motors are there. So you require three phase supply. So you require a three phase AC voltage controller, not the single phase AC voltage controller. This is one of the circuit diagram. Okay, now we'll see some more circuit diagrams. Some more circuit diagrams having um, you see now that you see here. So based upon that, whether it is star connected or delta connected, it will be decided like that. No, I'm just drawing several options are there to have. So then several possibilities of AC voltage controllers. This one is stator windings. Now you see here in this AC, this is also a three-phase AC voltage controller. If you see here, so what you find out here is that you find out one thyristor, one diode. This is also one type of AC voltage controller. This is also one type of AC voltage controller. So, so and the stator is now connected as the stator is now it is a star connection here. Okay. So these are the changes you will find out. The changes you will find out. Okay, some more. You have so many like this, so many possibilities are there. Okay. So the same one, instead of having thyristors, instead of having thyristors, instead of having diodes, here I will put this here. So now we will have thyristors. Thyristor, we have thyristors. So what is the difference between this picture and this picture? The difference is that here you have one thyristor, one diode in anti-parallel. Here you have both thyristors in anti-parallel. So that is the difference between these two pictures. This is also another type. So we are discussing several types of. We are just going through several types of AC voltage controller. Nothing else is there here. Okay. Now I will draw another. Say for example, you have the stator is connected in delta, not in star. Then in that case, what is circuit diagram? You will find out. In that case, what is the circuit diagram? You will find out. So this is another thyristor. So you can only thyristor. So the stator is now delta connected. Okay, so same. So this circuit diagram, both are same, except here you have the stator is delta connected. So three phase. So we are drawing several circuit diagrams of three phase AC voltage controllers. Okay, you can draw some more also some different ways you can draw. There is nothing in this wrong. Okay, so each one has its own advantages and disadvantages. Okay. But only thing is that what you need to understand is that what is the output of your AC voltage controller. This is another one. This is another types of AC voltage controller. So you have three-phase supply here. See now this is another type of AC voltage controller. So all these things we have done. Okay. So so I hope I don't need to tell the operation of the AC voltage controller because this we have done already in the power electronics course. Okay. Just I will draw the waveform of single phase AC voltage controller. Now instead of having I hope you know this thing also. Instead of having two anti-parallel thyristors, instead of having two anti-parallel thyristors, you can have one triac. One triac is also there. This also, one triac is nothing but what is a triac? What is there in a triac? Anti-parallel connection of thyristors. Anti-parallel connection of thyristors. So one triac is nothing but anti-parallel. So give single phase supply. Then what is the circuit diagram you will get if I mean what is the waveform you will get? now you see. So supply voltage Vs. Here is your supply voltage Vs. Um, yeah, this is your supply voltage. So now assume that the firing angle is alpha, and alpha is here. So what do you find out here? The waveform. What do you find the waveform here? The waveform now will be like this. So here is your alpha. Here you have another alpha equals 180. That is for the other resistors. So now you see, we just so then so this is your output voltage. So this is V naught is the output voltage. V naught is here. So now you see the V naught output voltage. Of course, it is AC, but it is not sinusoidal. So this is the point you must keep in your mind. That's so. So by knowing the RMS value of this equation, this waveform that we might have derived already in case of the Fourier transform. So you see that RMS value is a function of alpha. It's a function of alpha. So as it is a function of alpha, if alpha varies, the output voltage, that is the RMS output voltage, also varies. It means the stator voltage varies. So this is the logic behind this AC voltage controllers. So here the principle here is that by varying the stator voltage, you vary the torque. So the question is that how do you vary the stator voltage? One way is that you can have this AC voltage controller. Several types of AC voltage controllers also there. Okay. So using all these controllers, okay, we can vary the uh, we can vary the stator voltage. So by varying the stator voltage using those equations, we can do something. Okay. So now with this method, what are the advantages? What are the main advantages we'll see now? First of all, the control circuit is simple. You see, you don't have much. You have only some thyristors are there. You have only some thyristors are there. If there is only two or if it is three phase, you have six thyristors. Or you see the half wave AC voltage controller. If you see the half wave AC voltage controller, you see only three thyristors are enough. So it's a simple, comparatively it's a simple circuit, and at the same time, the triggering circuit also very simple for the thyristors. Okay, they are readily available. So one advantage we can say is that the control circuit is simple. And second thing is that uh, so now you see now another advantage is that converter size and weight is less. Okay, why the converter size is less? Is a simple thing to understand that. What do you have here? Here you have only few number of thyristors, that's it, and the triggering circuits of those thyristors. So if you even go to the market, you see the thyristor, simple thyristor, of course, even though the power is higher here because they are three-phase induction motor. So So thyristor circuit is comparatively okay, and you don't have much, you don't have any other components other than thyristors if you go through the circuit diagram. So we can say this thing that the size is less and also weight is also less. That's another advantage. Okay, and it is economical. Another one is that it is economical. Economical, same. Okay. See, first advantage, second, third, and all the three have relationship. So that's simple. And another one is that the response also is quick. Why the response is quick here? Why the response is quick here? Immediately, whenever you want to change the output voltage of the converter or the stator voltage, you simply change the firing angle. Okay, you might have seen in the laboratory also how you change the firing angle. You just recall yourself that you can change the firing angle. So there is a control system laboratory. You have some kits are there where you can change the firing angle. Or even the power electronics laboratory also there are some knobs are there, simple knobs where you change the firing angle. So as soon as you change the firing angle, so this process will take in less time. So that is also advantage. Now what are the so it has some disadvantages also. I will tell you disadvantages. What are the disadvantages? That first thing is that your input power factor is low. This is very main disadvantage. How do you say input power factor is low? Now you see what is the output voltage here? The output voltage is, you see the output voltage is a non-sinusoidal. It's a non-sinusoidal. So if it is non-sinusoidal, the output current is also non-sinusoidal. You see here, see here, you see here the output voltage I have drawn. So the output current I also non-sinusoidal. If it is non-sinusoidal output current, if it is non-sinusoidal output current, then you will find out the input current is also non-sinusoidal, because if you see this particular circuit diagram, output current is same as the input current. So it is also non-sinusoidal. So if it is non-sinusoidal, okay, then if you draw the fundamental, so I hope you know how to find out the power factor. So power factor you can find out from the supply voltage, the phase difference between the supply voltage and the fundamental component of the supply current. As the supply current is non-sinusoidal, you have to take only the fundamental component of supply current only. So when you take the fundamental component of supply current, you will know very well that there is a difference between both the waveforms, voltage and current waveforms. So when there is a difference, when there is a phase difference between both the waveforms, it means the power factor is low. That's the meaning of the conclusion of that. So, and another thing is that other thing is that the other disadvantage is that efficiency efficiency is low. Why the efficiency is low here is that, okay, why the efficiency is low here is that because of this voltage distortion, you will find out some harmonics, you will find out. And apart from the fundamental component, even the harmonic components also will contribute to the power loss. So power loss is more comparatively. So when the power loss is more, then the efficiency is low. Okay. And third thing is that, see, using the AC voltage controller, I hope you know, for example, supply voltage is Vs. V0 is the output voltage of the AC voltage controller. So what is the relationship between these two? I will say this, that V0 is always less than Vs. This we have seen. V0 is always less than or equal to Vs. At max, the output voltage is equal to supply voltage. So it means here using the AC voltage controller, the stator voltage is less than the supply voltage, not more than the supply voltage. It means using the AC voltage controller, you just reduce the stator voltage. You will not increase the stator voltage. That is the thing. So if you reduce the stator voltage, what is the problem is that it's not a problem, but sometimes it's a problem. What is the problem? If you reduce the stator voltage, then then what is the thing you will find out here is that if you reduce the stator voltage, if you reduce stator voltage, because using the AC voltage controller, you can only reduce the stator voltage. So if you reduce the stator voltage, then sometimes because of the reduction in the voltage, the torque, the torque production, the torque production, okay, okay. So please answer. Is it visible? The screen visible? Please answer. Anyone?
Yes, sir.
Okay, okay. Thank you. Someone I just thought that it is not. Okay, now you see now. So one of the disadvantage we are discussing. What is the disadvantage is that I said now that as the AC voltage controller output is always less than the supply voltage, it means using the AC voltage controller, you are reducing the stator voltage. You are not increasing stator voltage. So when you go on reduce the stator voltage, one problem you will face is that maximum torque is there. This maximum torque is function of stator voltage. So as you reduce the stator voltage, maximum torque of the induction motor also gets reduced. That's the problem. If the maximum torque gets reduced, then this method may not be useful for the heavy loads, because heavy loads you need high maximum torque. So that's a problem. That's one more disadvantage. That's not one you can say like this. Okay. So another thing is that the performance of the machine. Yeah, this is fourth one. So third one is that maximum torque gets reduced at reduced voltage, stator voltage. Okay, this is third one. Fourth one is that performance of this is poor under under low speeds. Low speeds. Okay. Also at low speeds. So the performance of this system is poor at low speeds. Why it is so at low speeds? At low speeds, what you find out is that at low, because why you are going for low speeds first of all? Because the stator voltage is less. So as the stator voltage is less, obviously, okay, the power going to your induction motor is less. So when the power going to this your induction motor is less, then obviously you will run the motor under low speed. So induction motor under low speeds, okay, it's not it's not advantageous. It's not advantageous if you run the induction motor at low speeds. Okay, so why it is so in the sense you recall the torque speed characteristics. In the torque speed characteristics, okay, so this is torque, this is speed. You just recall that. So this is low speeds. So under low speeds, you know very well that this part is unstable part. Okay, so that's what I'm saying. The performance is not good. Performance is poor under low speeds, because you generally use this AC voltage control method. Okay, for the reduction of stator voltage. So this is another. So every method has its own advantages and disadvantages. Okay, then we'll do one thing. Then we will see. We'll draw the block diagram. The closed loop diagram will come. I hope you know in all electric drives, okay, so you require closed loop only, not the open loop, because it's entirely automatic. So first I will draw the AC voltage controller. Okay, so this is three-phase induction motor. Three-phase induction motor. three-phase induction motor. So then the coupling is there. Coupling in this is this, there is some load is connected, and uh, it runs with some speed. Okay, so here it is a three-phase DC supply. Then what is closed loop here is that we will sense the speed here. Okay, how do you sense the speed? I told you using a sensor. In this case, the sensor is tacho generator. So tachometer you have seen already. In the lab. Tacho generator in the sense, yeah. You see, MTech Power Electronics course, MTech Power Electronics laboratory is there. When you get a chance, you go and visit there. There you find out a tacho generator. Tacho generator is a sensor. It generates some voltage. It generates some voltage. Okay. It generates some voltage. Nothing else. So I told you even in the previous classes, I think I might have told you this thing that sensing is nothing but a sensor. What it does, it converts a physical quantity to electrical quantity. This I think I have told you already. So it generates some voltage here. Then actual speed is there here. It is also in voltage. It is also in electrical quantities. The actual speed which you require for which you want for your uh, induction motor. So both will be compared here. Then there will be error. Then you will have an amplifier here. What is the purpose of this amplifier is that it amplifies the power of the signal. The power of the signal will be very less because the error signal has low power. Then you amplify its power so that it will have a considerable value. Then here you have triggering circuit, triggering circuit, triggering circuit of the thyristors. Okay, so then it gives signals. So total six thyristors are there. So total six thyristors are there. So it generates six signals. That's it. So now this is the block diagram. So based on how much speed you require that you set, I'm sure that you have come across this even in the power electronics laboratory that you set some speed based upon the speed. Okay, then it will compare with the actual speed using Staco generator. Then you have got some error. Then that error will be amplified. What is the purpose of the amplifier here is that to amplify the power of the so this power of the error signal is less generally. So when the power of the error signal is less, then it may not sufficient to drive this triggering circuit. So you amplify it so that the power increases. Then after that, that error signal, amplified error signal will go to the triggering circuit. So in the triggering circuit, you have this entire topology. Then based upon that, it generates the firing angles. These six signals will go to the six thyristors. So the firing angles will go like this. So that's it. So you control and you make. So this is a closed part. So you control and you maintain and you regulate the speed of the induction motor using this block diagram. So then you have another type of AC voltage controller that also we will discuss. What is that thing? Is the four quadrant AC voltage controller. So what is four quadrant AC voltage controller? Is that we have seen already even in case of the chopper, or in case of the DC motors. What we have seen, we can run the DC motor or we can operate the DC motor in all the four quadrants. We can operate in all the four quadrants, and we have seen this thing also very well. What is that thing we have seen? Is that in the first quadrant it is motoring, third quadrant is also motoring, but it is forward, it is reverse motoring. Whereas this case it is braking, it is also braking, forward braking, reverse braking. This we have seen. So when it is braking, the power is negative. So when it is motoring, the power is positive. This also we have seen. So the same thing can be achieved here, like which we have achieved using the chopper in case of the DC motors. Using this four quadrant AC voltage controller, we will achieve this four quadrant operation of the induction motor. Okay, see how we will do that. So just it's only circuit. So now is why three phases are there. This B. So we have the induction motor here. This is a normal three-phase AC voltage controller. But now this, what is this four-quadrant AC voltage control is that? I will tell you. First, let me draw the circuit diagram. Then I will tell you the logic behind why. What is that thing actually? So how can you drive that into four quadrants? See, driving into four quadrant indices, what does that mean? It means that I hope you know that first quadrant, the torque is positive, speed is positive. Second quadrant, okay, second quadrant also it depends upon which you have taken an x-axis, which you have taken an y-axis. Okay, so whereas third quadrant we can say both torque and speed are negative. Both torque and speed are negative. So here our job is that what is our job is that we have to make sure that it operates in all the four quadrants. I just do this connection. Okay, so I will call this as B dash. Why I am calling this as B dash is that it is connected to B here and R. Then I will have another set here. So two extra, total four thyristors you add extra here. Okay. Then this we call it as R dash. So it should be connected to R. How can I connect this into R? Yes. So now you see now. See here, what you need to understand here is that there is a logic I hope you know RYB phase sequence and RBY phase two types two phase sequences are there. So when you change the phase sequence, what do you find out when you change the phase sequence? You just imagine yourself when you change the phase sequence, what is the thing that is going to change? I hope you know in case of your induction motor also, whenever you change the phase sequence, the motor gets reversed. The motor gets reversed whenever you change the phase sequence. Okay, so what you do here is that okay. So what exactly you are going to do here is that by changing the phase sequence. So one phase sequence RYB, you will operate in first and fourth quadrant. You will operate at first and fourth quadrant. You can operate in first and fourth quadrants if you use one phase sequence, RYB phase sequence. I can say this thing. So I will say this thing that when you use one phase sequence, it is in one first and fourth quadrant. Whereas if you operate in another phase sequence, it will be second and third quadrant. So this RYB phase sequence I will write here. In this case, it operates at one first and fourth quadrant. So first and fourth quadrant in the sense both motoring and braking. This is motoring. This is braking. This is braking. Whereas this is motoring. So this you call it as reverse motoring. Okay, reverse motoring. So that's what I'm saying that you see here in this case one variable is totally positive. One variable is totally positive. So say for example, this is speed. This is torque. This is speed and this is torque. You see here what you will understand here is that during this case, okay, your torque is always negative. Whereas during this case, the torque is always positive. So as the torque is always positive, the torque is always positive here, whereas the speed reverses here. Here also speed reverses here. So by changing the phase sequence, because I am sure that reversing a motor, okay, okay. Otherwise you got to take this as This is torque and this is speed. Torque and speed. See this case, first and fourth quadrant, the speed is positive, whereas second and third quadrant, the speed is negative. So minus omega plus omega. So when the plus omega is there, when you will have plus omega, when 1 and 4 quadrant are operating. When you have minus omega, when 2 and 3 are quadrants are operating. So how do you make the speed reverse here, or how do you make the speed? How do you make the motor in to run in the opposite direction? So how do you do that? How do you do that? Is that by changing phase sequence? This you have studied in case of the three-phase induction motors. So three-phase induction motors, by reversing the phase sequence, you can reverse the motor. So reversing a motor using using phase sequence. So by changing the phase sequence or by reversing the phase sequence, you can reverse the motor. That is the logic behind it. So how do you achieve that? How do you achieve that? Is that simple thing that you see here? You have the thyristors here. So this, so in when you want to operate in 1 and 4, when you want to operate in 1 and 4, you go for this black color. This one, and this one. These three set of thyristors operate. You don't turn on B dash and R dash. You don't worry about B dash and R dash. Simply you make them off. Okay, don't give any kind of triggering pulses to B dash set and R dash. So don't give any kind of triggering pulse. You operate only these three sets which are in black color. Okay, then in that case you can run induction motor 1 and 4. 1 and 4. That is by in motoring and also in brake. You apply some brakes, then also you can do. Whereas you want to change the phase sequence, because then only you can reverse the motor. So how do you change the phase sequence? Is that simple thing. You trigger B dash and R dash transistors along with Y. You see here, you trigger B dash, R dash and Y. So when you do that, what is the phase sequence? You will find out. You will see the phase sequence gets reversed. That's it. So when you are operating this red color, you make sure that this R and this B are turned off completely. So otherwise, dead short circuit will occur and it will damage the entire drive. It will damage the entire induction motor drive. So here that is the reason that we add two more sets of thyristors here. One is connected to B dash, the other is connected to R. One is called B dash, the other is called R dash. So it is connected to R here. So you see the connection here. That's it. So when you see the connection, you have to imagine yourself that when do I turn on these thyristors? So if I turn off this and I turn on this, then which terminals you will find out here? Here you will find out B. So when I turn on R dash, by turning off this, which terminal you will find out here? R. So you will find out B Y R. Earlier it is R Y B. Now it is BYR. BYR is nothing but RBY. That's it. So that's the phase sequence. So here, better I will write this here. RYB. If it is RYB, then you operate RYB set of thyristors. If you want to change to RBY, you operate, which one you operate first? B dash will come here. Okay, then Y remains as it is, then R dash. So that's it. So when you change the switching sequence here, we can reverse that and you can get the required all four quadrants also. You can get that. Okay. Then we'll do one thing. Now you see, within 2-3 minutes, I will complete a numerical problem. Okay, so yeah, this is a numerical problem. Please see this now. Here 2200, 2200 volt, 2600 kilowatt, 735 rpm, 50 hertz, 8 pole, 3 phase, 12 case induction motor has the following parameters. Directly he has got the parameters: RS, R2 dash, XS, XR dash. So what is RS, XS? They are stator values. What is R2 dash and X2 dash? They are rotor values referred to stator. So it means the equivalent circuit, this one. This equivalent circuit parameters he has given. This is Rs, Xs, R2 dash, X2 dash. These values he has given in the problem. Stator winding is delta connected. Okay. Calculate the starting torque and motor torque as a ratio of rated torque. So you have to calculate the starting torque, maximum torque as a ratio of rated torque. So that's your job. So you require only what you require is that you require some formulae. So now see the formulae. I'm not going to derive right now because you have the formula already in the previous classes itself. So you just recall those formulas, then those formula you can use directly here. It is not necessary to derive the equations right now. So a rated torque, because we have to find out the rated torque, we have to find out the maximum torque, we have to find out the starting torque. Then we have to do the ratio between starting to rated and maximum to rated. So anyhow we have to find out all the three torques. So rated torque, what is the formula for the rated torque is that? Please recall. It is three. Uh, See, I will write directly. Just see this now. R2 dash, R2 dash by S. So this is the power whole divided by omega S. So this is the rated torque. We will find out of the rated values. 3 into. So what is the rated current? Everything we have to take rated. So how do you find out the rated current is? To find out the rated current, what we require here, how we find out the rated current. So please recall the equation for I phase. What is IP? IP is the I phase. So what is IP value? You apply KVL here, then you will understand yourself what is IP value. So what is that? Is that V phase divided by square root of square root of RS plus R2 dash by S. Okay, R2 dash by S whole square plus XS plus H2 dash whole square. This is your IP value. So we are finding out each one IP first. So IP, this is the formula. This is IP. So then what is VP here is the phase voltage. How do you find out the phase voltage? So now you see in the problem he has given, we are finding out the rated, so we'll take on all the rated values. So 2200 value, 2200 volts he has given. So what is that? It is a line voltage. I told you already that in three phase the voltage mentioned is by default it's a line voltage. So line voltage we have here, we have the line voltage here. So but we need here phase voltage. How to know, how to get the phase voltage? It depends upon the type of connection. What is the type of connection? He said stator is delta connected. So if it is delta connected, phase voltage, line voltage both are same. So 2200 whole divided by square root of RS. RS value how much he has given in the problem? 0. 0.075. Yes, 0.075 plus R2 dash value. What is R2 dash value he has given in the problem? 0.1. So 0.1 divided by S. Okay. What is S now? How do you find out S? So S is the slip at rated values. So how do you find out the slip at rated values? So first of all, you must know S is equal to formula. You have Ns minus Nr by Ns. This everyone know this thing. So what is Ns value? Ns value, how do you calculate? You just see whether he has given any data regarding Ns.
120 F by
Okay,
P.
so yeah, that's correct. Good. So we can find out Ns with this. Ns is equal to 120 F by P. So 120 into F, I think he has given 50. What is, yeah, 8 volts he has given. So 6000 by 8. How much is 6000 by 8? 6, 750 RPM. So we got NS as 750. 750. So you put here 750 minus. The next thing is the, what is rated speed? Yeah, 735 RPM he has given in the problem. See this. Yeah, this one. 735 RPM he has given. So we will put 735 here by 750. What is its value? So 15 0.02. So the slip we got 0.02. So then S value put here 0.02 whole square plus excess value. Excess value how much he has given? 0.45. So 0.45 plus 0.55 whole square. Whole square root. So this is the value of I phase. We need I phase now. So what is this value? Please do this simplification. So this it becomes 1. This is 3, so we got 25 plus this is 1. So 20 plus 1. We got this answer over square root. We got this
Sir,
1.
13.14, sir.
Yeah, thank you. How much? 4?
13.14.
Yeah, I got 425.31. You'll see this. 425. Oh, no problem. Okay. 425.31. Approximately same, no problem. That's not a big problem. So you got this answer. 425.31 ampere you got. So we got I phase. Then what else we require here? What else we require here? We require R2 dash. R2 dash is also we have already ready made. Okay. Then what else we require here? So S value also just now we have find out. See, one by one we are finding out. So one by one we are finding out here. I phase we find out. R2 dash we know. That is 0.1 is R2 dash. Whereas S value is also we find out that is 0.02. Okay. Then we need to find out this thing. So 3 into 425.31 whole square R2 dash is 0.1 divided by 0.02 whole divided by omega s. Omega s is nothing but I told you already that it's a synchronous speed. So, but you have to find out in terms of omega, that is angular frequency. So 2 pi n by 60. So 2 into pi into n is 750 by 60. Yes. Please tell me how much you got this. How much you will get this thing. So that's the rated torque. So square into 3 0.1 divided by 0.02 divided by 2 divided by 5 divided by 750 multiply with 60. So you got 3, 4, yeah, whatever the answer was, we'll write directly. So we got the answer 3, 4, 5, 3, 4, 5, 4, 8. Yes, this is the rated torque. Now we will find out the remaining two torques, maximum torque and starting torque. So what is maximum torque? Now I will write the formula directly. I just do one thing that you just go through the equations of the maximum torque. I'm sure you may get there. 3 by 2 omega s and then the equation here 3 phase square rs rs square plus xs plus x2 dash whole square. You can find out the formula yourself. There is nothing here. You find out the techniques of. So what you don't know here, everything in RS, XS, X2 dash, omegas, everything, please substitute it. I'll write down directly. 255 88 Newton meter. There is nothing, you don't find anything here. already we have find out. The next one is starting torque. So what is the starting torque like that? Okay. So what is the starting torque and actual torque formula? Only one difference. I guess why R2 dash by S by omega S. So starting torque is S is equal to 1. Nothing else is there. Then remaining things are same. We know R2 dash we know, then omega also we know. Everything we have. Difference between the starting torque and the rated torque is that in place of the rated torque you have S value 0.02, whereas here S is equal to 1. Because starting torque your speed is 0, so S is equal to 1. So we'll find out this also, starting torque. Substitute this, then we'll get the answer. See, I'm just leaving this substitution to you itself because of this time is not available, time is over already. So do the substitution and do the calculation yourself using the calculator. So we got all the three torques. So what is the now? What is the ratio of starting torque 5979.3 by rated torque? This one. Please, you have to find out this one. Then the second question is that what is the ratio of 25588? That is maximum torque to once again full load torque. 48.6. So these answers you have to find out. Only these ratios you have to find. Use calculator. Then we will get some answers here. Starting torque to this one is 0.173, whereas maximum torque to the full load torque is 0.80. That's it. These are the answers.